So far, all of the momentum problems we've looked at have been one-dimensional. I wanted to look at some two-dimensional momentum tips and do an example for you guys. So our momentum is a vector, just like force, just like velocity, which means that our momentum for an object, if this is a ball with a velocity up and to the right, it has momentum that is up and to the right, and that momentum has an x component and a y component, just the same way that the velocity of that object might. Now, if we have multiple objects with their own momentum vectors, we still want to be able to combine their momentums into the total momentum of the system if there is more than one object. So in other words, our total momentum vector is equal to the sum of all the individual momentum vectors of all of the I objects in our system. And how we do this sum, how we combine those together, is just like any other vector, and that means we have to take this equation in the x direction, which means the x component of our total momentum is equal to the sum of all of the x components of the individual things, and the y components also equal the sum of all the y components. This I is not supposed to be like initial. This I is like summing over the I different things that make up our system. So we don't have to worry about that if we don't want to. This equation applies equally well for the initial and final states of a problem. Now, how do we get the individual x and y components? Well, these are just, each of these px's is just the mass of the object times the x component of the velocity. So for each object, we can figure out the x component of the momentum. For all the objects, we can combine those x momentums into one big x component, and the total x component and the total y component are enough to tell us the total momentum vector of the whole system. So other than that, the approach to solving these problems is identical to the others. If we're trying to find, for example, a final velocity, knowing some initial velocities and maybe some other final velocities, we figure out what the total momentum in the system is, maybe again, if we know all the initial velocities, that's enough to figure out the total initial momentum. Say, the final momentum has to be the same as that, and then that lets us solve for the unknown velocity in that system. All right, let's do an example to see how this actually works in practice. While I'm erasing, 2D momentum problems are going to be a little different than 2D kinematics problems and 2D force problems. And the reason for that is our 2D momentum cannot be conserved if there is an external force on it. So for something like throwing a ball through the air, like we have done so many times, this is a great 2D problem from chapter 2, but we know momentum is not conserved for this problem because there's an external force on this object, right? Our momentum is never going to be conserved for something flying through the air because there's always this net external force on it. So our 2D conservation of momentum problems, they will always not have external forces. Which either means that we have to be doing something like in space where there's no gravity, but more likely these problems tend to be looking at a situation from the top view. So whatever gravity we have is like in the into the board direction, and it doesn't affect the x or y motion of our objects. So I'll say our problems will probably be what I would call a top-down view. And so you'll see what I mean by this with our example. Okay, so here's our example of a 2D momentum problem. So we have two skaters on a frictionless ice surface. And here is our top view of the skaters on the ice. So this area is the ice. We have a 70 kilogram skater moving to the right with a velocity of 5 meters per second. And we have a 90 kilogram skater moving down and to the left at a 45-degree angle with a velocity of 4 meters per second. So this is the setup. If the skaters collide and stick together, so maybe they run into each other on the ice and give each other a hug, or maybe one of them is covered in glue or something and they become inextricably stuck together. Anyway, it doesn't matter. They stick together somehow. What is their final velocity? And note, this is the final velocity of both of them. Since they will be stuck together, they will be moving at the same velocity. And we want to be able to give our answer in terms of components, right? So this velocity is going to have two components. We also could give this as a magnitude of the velocity and a direction. It turns out that's going to be slightly more work, so we're just going to worry about the components for this example. All right, let's go ahead and get started with this problem. I'll leave the picture up. So let's label these two people A and B. So we can talk about the momentum of person A and the momentum of person B. So let's look at person A first. Let's find a better pen. So person A has a velocity with an x component of 5 meters per second and a y component of 0. This lets us then find the momentum components. Px equals mvx, and the mass is 70. So 70 times 5 is equal to 350 kilogram meters per second. Py is equal to 70 times 0, which equals 0. All right, so we have our first two x components. I guess I should call these Pax and Pay just so we know that these correspond to person A. Person B, we have their velocity components. Well, we can figure out what their velocity components are, right? So their velocity vector is like this, 45 degrees. So our two components look like this. Those are going to be the cosine and sine of 45 degrees times 4. So Vx is going to be equal to, that's adjacent, so that's 4 times the cosine of 45. And our x velocity is to the left here, which means we need a minus sign. Vy is going to be minus 4 times the sine of 45 degrees. So this is also in the negative direction. And of course, the cosine and sine of 45 degrees are the same, so we're going to end up with the same numbers for these. So before I bother plugging these in, we're going to have to multiply them by 90. So let's just do all that at once. So Pbx is equal to 90 times minus 4 times the cosine of 45 degrees, and Pby is the same. So plugging these into our calculator, we get minus 254.6 kilogram meters per second. All right, so we have all of the pieces we need now. We have all of our initial momentum pieces. So now, I should have labeled, these are initial. So we can combine these and figure out what our total initial momentum is. So the sum of our, well, let's do it this way. Our total x component of our momentum is the sum of all of the individual x components, and that is this and this. So this is equal to 350 plus minus 254.6 kilogram meters per second, and that is equal to positive 95.4. In the y direction, we have the sum of our y momentum, so that is 0 plus minus 254.6, which is just equal to minus 254.6 kilogram meters per second. So these are the components of our total momentum. So we'll hold on to this for just a second and erase what's going on over here. So after these two people collide and stick together, they, so we have this person, they run into each other, and we end up with this thing that is both of the people, both people A and B, moving with some velocity. And we don't know what direction that is, but we would like to figure it out. And we do have enough information to draw that direction right now. And that's because we know the components of our momentum, right? So whatever our initial momentum is, that has to be the same as our final momentum, because our momentum is conserved. We don't have any external forces changing the velocity of these things. And so whatever velocity we have at the end is what's making our final momentum. So in other words, this picture is all that's going on at the end. So the momentum here has to match the momentum here. So in other words, whatever velocity we have here has to match the fact that these are our two momentum components. So for this final picture, we now know Px is equal to 95.4 and Py is equal to minus 254.6. And these are coming from a single object with mass 70 plus 90 equals 160 kilograms. And here we have a velocity that has a y component and an x component. So our momentum for this picture, like ignoring these numbers, our momentum for this picture is this mass times these components, right? Px is equal to m vx, py is equal to m vy. And because momentum is conserved, these values have to equal these values. So now, to solve for the velocities, we just have to divide these numbers by 160. So in other words, this is equal to that. So 95.4 is equal to Vx times 160. So Vx is equal to 0.596 meters per second. I'll erase this to make room for the next one. So our y momentum is minus 254.6. And this is equal to m vy. So vy is equal to minus 254.6 over 160, which is equal to minus 1.59 meters per second. So these are the two components of our final velocity for the combined mass that is person A hugging person B. So yeah, this is a pretty typical 2D momentum conservation problem. I think the component stuff should feel pretty familiar at this point. We haven't talked about energy at all, but if we did want to look at the energy of this problem, it would be just the same as our other momentum problems. We would just want to do a 1/2 mv² calculation for each of the objects we have in this problem. Yeah, other than that, I don't think there's a whole lot to say. It is important that there's no friction, and I will say why that is. So here, if we think about the forces on these people on the ice, gravity is pulling them this way into the board, and the normal force from the ice is holding them up, pushing them out of the board. But there is no force on them in the X or Y directions. And that is what allows momentum to be conserved in the X and Y directions. If there were friction, so like for example, for person A here, if person A had friction with the ice, or if they were on some other frictiony surface, we would have a kinetic friction force that was in the opposite the direction of movement, right? So here we would have a kinetic friction force that was to the left. This would be a net external force on the object, and as a result of that, momentum would not be conserved for person A anymore. So that's why it's important that we cannot have friction in these kinds of problems. If we did, that would be an external force, and so that would make momentum no longer conserved.